Hello guys, nice to see you. Okay, so my first question, did you receive my email, like message via Moodle about the upcoming midterm? Okay, good. So as I mentioned last time, be aware that the topics related to torque were angular cross product, so the cross product of vectors is involved, angular momentum, also kinetic energy of rotational moment, specifically this type of problems which involve vector product and rolling objects on the inclined plane. Double check that you had some practice on that, since it was the last topic, which is going to be included in the midterm 2. However, gravity, which we are considering this week, it will not be in midterm 2, so it will already be later. So prepare yourself and good luck with that. Hi, nice to see you guys all here. Okay, I guess we can continue our discussion. Last time we stopped on introducing the gravitational field as some substance via which the interaction between bodies can happen even without putting them in direct contact with each other. Okay, we have a question about midterm. So from the email, like message which I sent via Moodle, you can see that you will have 60 minutes as usual, but as a bonus now, you will get 10 minutes extra. So in total, you will have 70 minutes to solve the problems. And these 70 minutes should be within that time frame which is assigned. So yeah, you will have 7 problems, as I remember, and 70 minutes to solve them. Yeah, but again, I guess some people joined recently. Again, I strongly recommend you to double check and revise in your memory the last topic, vector product and rolling on inclined plane, which involves kinetic energy of rotational moment, like angular momentum, torque, because this will be included there. And since you didn't have long time from this discussion of this topic until midterm, be aware that you need to practice and solve these kind of problems. will definitely help you. Okay. So let's come back to our discussion. As I mentioned before, we considered that one of the biggest problem and concern regarding the proposed universal gravity equation by Newton was that people couldn't understand how is it possible that objects which are not in direct contact with each other still can interact and experience this gravitational force. Well, only later was proposed the concept of gravitational field, and that gravitational field is some effect of each body which has on space around it, because it creates this gravitational field. And if within this gravitational field there is another body, there will be certain force which acts via this gravitational field on this body, external body. And that force will be directed to the origin of this gravitational field, means directed towards the body which form the gravitational field around it. And it's a fundamental feature of all matter. If they possess any mass, they create this gravitational field around it, and this is the mechanism which can explain the interaction between different bodies which are not in contact. I mean, so there is a question if the gravity is considered as a force. I mean, force is a result of gravity, of the presence of gravity. When you have gravitational field and some mass, you end up with an attraction force which acts on this mass. However, gravity could be considered as, in our case, in the case of classical mechanics, it's considered as a vector field, vector, because it's not just some scalar number. It also matters. So we don't have just some distribution in space of scalar numbers. Like it doesn't tell us much. It's a vector field because in every point of space we have a certain vector which describes the property of this gravitational field in this specific point. And that is strength, so-called strength of gravitational field, and is measured in the acceleration of free fall. But that is not just number, it's vector. So it's always directed to the center, to the place where the body, the origin of gravitational field is located. And that shows us in which direction gravitational force will act on any body if we put it in this point of space where this gravitational field exists. So it will be always attracted to the origin of this gravitational field. Okay, so if we are talking about gravitational field and its potential field, so it this force, gravitational force, depends on the distance from the origin. Definitely, it also we can describe it also in terms of potential energy as a function of distance from the origin. So that's exactly what we are planning to do right now. And then once we introduce the potential energy of gravitational field, we can proceed further and consider motion of bodies, or for instance, planets about the sun, taking into account the sum of kinetic and potential energies. So we will see what will be the total mechanical energy of these planets moving about the sun, or it can be applied to any other objects. It can be some artificial satellite which is moving about the Earth. It doesn't matter. So the concept will be generalized and applicable to any system, like isolated system, which interact only within the gravitational field. Okay, let us change the screen. And as I mentioned before, if we assume that there is some body with certain mass, then at any place in the space around this body, it creates gravitational field, which is a vector field. And this gravitational field in each point will be described by a vector quantity, acceleration of free fall, which in terms of gravitational field is considered as a strength of gravitational field. So it's G vector equal to gravitational force which will act on some body M located in this gravitational field and divided by its mass. So we kind of cancel out the mass from equation for the gravitational force, and in vector form it will be minus capital G, which is a gravitational constant. Sorry, it's not Earth, it's just capital M divided by R square, which is the distance, radius vector distance between the big body and small body, and the unit vector of the position vector, which gives us the direction, and this minus tells us that gravitational field acceleration of free fall, the strength of gravitational field, is always directed towards the center, or towards the origin of the gravitational field, which is this body with the mass capital M. Okay, so now let's go for potential energy. So we know by definition that change of the potential energy is difference between the final potential energy minus initial potential energy. It's defined by the location, final and initial position of the body in the external gravitational field, will be equal to minus integral when we move from initial position with radius vector Ri to final position with radius vector Rf of a potential force. In this case, it's gravitational force as a function of position, dr, as a function of radius vector times dr. So now we need to figure out what is this function, and this is, we already know this because it is the gravitational force, which is described by the universal gravity law. So let us write F as a function of R is equal to minus G, capital G. Let's consider now to be more related to some real system. Let's consider some our Earth. So it will be mass of our Earth. Then it will be more clear how we will do these calculations. So we have capital G times mass of the Earth, then times mass of some object around which moves about the S, and then we have R square. So this is expression for the force, which gravitational force as a function of R. And here this minus tells that this is attraction force, so it will be always directed towards the Earth. So in this case, let us proceed further with the calculation of the gravitation of the potential energy of gravitational field. So final potential energy minus initial potential energy will be equal to minus G, capital G, mass of the Earth times mass. Then, since all these are constants, then we have integral from Ri to R final of the R divided by R squared. So we get G M E times M. When we integrate, we will get, so here we have minus, will be 1 over R, and this will be from Ri to R final. Okay, so then we keep this minus here for a moment. M will be 1 over R final minus 1 over R initial. And assuming, so this is pretty much already the potential, change in the potential energy. And if we assume some boundary condition that at R distance going to infinity, so if the object is moving away from the Earth to infinitely large distance, then potential energy will be equal, like approaching to 0. So this is all about, as we were talking before, it's all about defining potential energy, some reference point. We can always define it in different way, because what really matters is the change in potential energy. However, to be consistent, it really makes sense to define some point which corresponds, some location which corresponds to zero potential energy. And in our case, makes sense to set this condition when distance from the Earth goes to infinity, potential energy also goes to infinity. So then we can write the potential energy as a function of R is equal to minus capital G mass of the Earth times mass of the object divided by R. So this is the equation which describes potential energy of gravitational field when we have, for instance, Earth, which creates gravitational field around it, and locate certain object with mass m in this gravitational field at the distance r from the center of the Earth. Okay, so let us write this equation on a new slide. And so this is R. And this minus tells us that we have some energy to be done to move the object from the Earth, from its current location to infinity, where potential energy is equal to zero. And that is because gravitational force is always an attractive force. So it always attracts this body closer to the Earth. And if you want to, from current position, move it to infinity, this work, which is equal to the potential energy of interaction between Earth and this object at the distance r, should be done to let it happen. So if we have a system of bodies, for instance, we have 3 bodies. So far we were considering only a system of 2 bodies. If there are more bodies, for instance, like 3, let's say we have body 1, 2, and 3, and we have distance between all these bodies, which is R1, 2, R2, 3, and R1, 1, 3. So in this case, gravitational potential will be a superposition of all potentials, gravitational potential energies, which originate from interaction of every body of each body with every body involved of this system. So it will be potential energy total equal to potential energy originated from the interaction between body 1, 2, plus potential energy originated from bodies 1, 3, and potential energy 2, 3, which is equal to minus G, capital G, M1 times M2 divided by R1 1, 2, then plus M1, M3 divided by R1, 3, and plus M2, M3 divided by R2, 3. Okay, so this is the way how you can calculate total potential energy of a system of bodies which interact via gravitational field. Okay, so now we can come to this point when we consider motion of planets and satellites in terms of energy, like kinetic total mechanical energy, which means sum of kinetic and potential energies. So let us consider some object with mass capital M, then at some distance, which is defined by the radius vector, we have another body with mass M, which moves about this central heavy object with circular orbit and has some linear velocity v. Okay, we make an assumption that mass of the central object is much larger than mass of the satellite. So let's call this satellite. So total energy will be the sum of kinetic energy plus potential energy. And let us write the expressions for these kinetic and potential energies. So kinetic energy is given as 1 divided by 2 m times v squared. Then we have minus, because potential energy is negative, as we derived before. Capital G, capital M times M divided by R. Okay, so we have now expression for total mechanical energy of this system. And you see that it's so far it's not very clear. It can be, since this one is positive, this one is negative, then result can be either positive or negative or equal to 0. So it's not clear from this equation how written in these terms how what will be the total mechanical energy. So let us rewrite this equation on a new slide and try to figure out what is there. 1/2 mv squared minus g capital M divided by R. So what we can write, since this like circular orbit is stable, this satellite is moving about this central body with stable circular orbit, we can write that gravitational force is equal to ma, where is centripetal acceleration. So they compensate each other and we have a stable orbit. So from here, assuming this, for gravitational force we write the universal gravity law, which will be G m times m divided by r squared equal to m, and for the centripetal acceleration, it's v squared divided by r, where v is linear velocity. So now what we can do, let us multiply left and right side of this equation with r divided by 2. And we will end up with the following picture. It will be G capital M times M divided by 2R. So we cancel out this square and add 2 in the denominator. And this will be equal to 1 divided by 2 mv squared. So from the right side, it's nothing else as kinetic energy of the satellite. And now we can express kinetic energy of the satellite in terms of gravitational constant, mass of the central body, and distance from the central body to the satellite, r. So that is good because now we can substitute, instead of this kinetic energy, its expression. Let us do it. So total mechanical energy is equal to G capital M times M divided by 2R minus G capital M times M divided by R. So what do we get? It will be equal to minus, since this part is twice larger than this part, it will be minus G capital M times M divided by 2 R. And this is expression for the total mechanical energy of a satellite which moves about the Earth or the Sun with some circular orbit. The similar can be shown for more general case when we have elliptic orbit. So that will be equal to minus G capital M, M divided by 2A, where A is the major semi-major axis of the ellipse, of the elliptic orbit. However, as I mentioned, most of orbits of the planet about the Sun are quite close to circular orbits. So this is important equation. So we understand from the result of total mechanical energy that it's actually negative, which means that this system is stable. This system requires some external work to be done on the satellite, or for instance on the Earth with respect to the, which rotates around about the Sun, to move it away. So that's why we don't fly away from the Sun. That's why our moon doesn't fly away from the Earth. because total mechanical energy of satellites which are moving about the some bigger bodies remains negative, and this is important factor which provides stability of such systems. So what is also important to know that this total mechanical energy, since the system is isolated, it doesn't interact with other systems. So this, if we consider two bodies isolated from external environment, this total mechanical energy will be conserved. So there are two major parameters which are conserved for planetary motion. We were talking about this earlier. It was angular momentum, and also total mechanical energy is conserved. So we can write that 1/2 mv square initial minus g capital M times m r initial is equal to 1/2 mv final square minus g m r final. So this is the conservation of mechanical energy of isolated system of two bodies which interact with each other via the gravitational field. Okay, so once we already defined the potential and total mechanical energy of bodies in terms of interaction via gravitational field, we can proceed further and consider some interesting cases of their interaction, possible interaction. So let us consider again the Earth. So this is our Earth. It has radius RE, and from this point, like from the surface of the Earth, now we don't consider any motion of the Earth, like rotation about its own axis or rotation about the sun. It's just only the mass, the planet itself, the gravitational field which is created by this planet. So let's say from here we have some projector which is launched with some velocity, like initial velocity upwards. And this will be the height this projectile will move from the surface of the Earth. And its location can be then described by, so let's say this is our velocity, and this is our R max, the radius vector which describes the final position of the body when it will reach the highest point of its flight over the planet's surface. So let us consider that we have certain distance we want this projectile to reach. Let's say we specify this R max, and we want to know which velocity, initial velocity, the body, the projectile, should gain in order to reach this position. So let us first write we can start from considering the conservation of total mechanical energy. And this will look the following. So what do we have initially? We have kinetic energy because we have initial velocity. It will be 1 over 2 m. So this projectile has some mass. So this will be our m. mv initial square minus potential energy it has on the surface of the Earth because of the gravitational field. So this will be gravitational constant, mass of the Earth times mass of the projectile divided by radius of the Earth, because initially it's on the surface of the Earth. So this is equal to the final position. At final position, when it reaches R maximum, there is no kinetic energy because velocity will be 0. And we have only potential energy. And this is minus G, mass of the Earth, mass of the projectile divided by R maximum. So just to make it clear, this is equal to R maximum is radius of the Earth plus this height. It will move. I mean, quite obvious, but just to clarify this. Okay, so now we can calculate for the initial velocity which will be required to reach this R maximum. So V initial square will be equal to, so we need to move this to the right, and let's maybe do it in 2 steps so not to lose anything. So kinetic energy will be equal to Gm, mass of the Earth, then mass of the projectile, 1 over with this minus and minus, we will cancel out the minuses, and then it will be our radius of the Earth minus 1 over final radius, R max. Now we can express our initial velocity as square root of 2 times G mass of the Earth. Here we cancel out these masses, divided times 1 over radius of the Earth minus 1 over R max. Okay, so as you see, this initial velocity to launch the projectile from the surface of the Earth to certain radius from certain distance from the Earth's center, R max, is not dependent on the mass of the projectile. So it can be just a bullet, or it can be some huge satellite. So doesn't matter what is the mass of the object. So obviously, we also don't take care here into account the resistance of air. So we assume there is no atmosphere. But if we consider only gravitational interaction, then the velocity which is required will not depend on the mass of the object and will be defined only by gravitational constant, mass of the Earth, radius of the Earth, and final radius where we want to locate our projectile eventually when it stops moving. So now we can consider some special case, so-called escape speed or second space speed. Escape speed is the speed of this projectile, which is required to move the object away from the Earth completely. So R maximum approaches infinity. If that is the case, then escape speed for the projectile will be equal to square root of 2gm, or mass of the Earth, divided by radius of the Earth. Yeah, so what we actually see here, that the escape speed is defined, since g is a constant, is defined by the mass of the Earth and its radius. So the larger mass, the larger will be escape speed, and the smaller radius, the denser material of the planet, it also will result in the increase of the escape speed. So, for instance, for escape speed for Earth, does someone know this number? What is the second space speed for the Earth?
Is it 7.9 or?
That is first space speed of the Earth. So it requires to you need to provide this speed to an object to create a satellite around which will move about the Earth in the space. And the second, which is escape speed, second space speed for the Earth, is 11.2 kilometers per second. So if you provide this speed without considering also the direction of motion, like rotation, like location of the launch, actually, if it's launched from the best approximation, it will be launched from the pole, like either north or south pole, like upwards, as it's shown on the figure. Then it should be 11.2 kilometers per second. For instance, for Jupiter, this second space speed is 60 kilometers per second. And you understand that it's already a huge challenge to send satellites from the surface of the Earth with escape speed like almost 6 times smaller than from the surface of the Jupiter. I mean, it doesn't have defined surface, it's a gas giant. But imagine if it's some solid planet, then it would be beyond these capabilities of chemical fuel, which we use for our rockets. So could be that at certain mass of the planet, of the Earth, we wouldn't be able to go to space by using current technology, just because it will be beyond the physical capabilities of the repulsion motion created by burning fuel in the rocket, because it would be not enough to provide enough high speed to overcome this barrier of escape speed. And talking about some extreme cases, that is black hole. So there are different options for the development of stars and in different stages. So in these cases, when stars are very heavy, usually much heavier than our sun, and after the supernova explosion, when the fuel of the star is already gone, if the mass of this blue dwarf, which is remained as a nuclei of the star, is larger than 3 masses of the sun, about this, then because of gravitational collapse, it can convert to first neutron star when pressure is so high that electrons just literally fall on protons in the nucleus of in atoms, and protons lose their charge and convert to neutrons. So literally we get about 10 kilometer in diameter neutron star, which the density of nuclei of atoms, because it's packed from neutrons. And then further gravitational collapse, when mass of the object is big enough, could cause the formation of a black hole. And then black hole, why it's called black? Because at certain distance from the black hole, the escape, which is called, so if we consider this as black hole, at certain radius about this black hole is located so-called event horizon. And this is the radius which defines this position of event horizon. It's the distance at which escape from the black hole, at which the escape speed becomes larger than speed of light. So then it's not just some limitation of chemical fuel repulsion force. It's fundamental limitation because we don't have anything what can move faster than light. So if any photon, which moves always with the speed of light, appear to be closer to the black hole than this event horizon, it will never come out from the gravitational field because its velocity, like speed, is c, like speed of light, and it will be smaller than escape speed. So that's why every information, including light, like, and objects, obviously, which appear to be closer than event horizon to the black hole, they will never escape because it's physically impossible. So that is some discussion of an extreme case of gravitational field when potential energy of gravitational field next to this extreme object is so high that even light cannot escape from this gravitational field. Okay, I guess with this we summarize our chapter of gravitational of gravity and gravitational field. And if you have any questions, you're welcome to ask them on Monday. Oh, there is a question. Clarify one thing. Should be considered total motion. Okay, I'm not sure I got the question correctly, but if there is some question regarding the moment of inertia of Earth, it should be moment of inertia. You should calculate it or use equation for the solid sphere with the radius r, which is radius of the Earth, because we don't consider Earth as a hollow sphere, at least if it's specified. I mean, obviously it's not uniform, but we assume that for many cases that could be considered as uniform, and specifically for solving some problems, usually it's considered to be uniform. But again, it depends on the parameters which are given in the specific problem. So usually it is a solid sphere, and that's why you need to consider the moment of inertia calculated for the solid sphere, but definitely follow the instructions in the problem. Okay, so we are running out of time now, and I would like to remind you again, on Saturday you have the midterm 2. Prepare for that and good luck. Have a good weekend and see you on Monday.
Mr. Bruce, Bruce, I have a bit of an off-topic question. So, like a month ago, I couldn't see the midterm exam since I had issues with my teeth. I don't know if you remember, but I texted you. So for the same reason, I couldn't finish the long kappa that week. It was week 4 homework assignment, like the 20 problems that you gave us. And I would like to ask, like, do I have any of the long kappa homework assignments that we can drop, or will I just get 0 for that?
Yeah, so we agreed that the lowest grade for homework assignment will be also dropped in order to address this possible.
Oh, okay, got it.
Internet or health issues or whatever.
Yeah, so, if you need, like, I have all the evidences that I visited the doctor that
but
anything should be sent.
That's okay. I don't need them. So okay. That be true for everyone. In order to address these possible issues, we drop the lowest grade for midterm and lowest grade for the homework. So So don't
Okay,
worry.
thanks. Got it. Thank you. Bye.
Mhm. Bye. Okay, guys. Have a good.
Sorry, can I ask a question?
Yes.
When are we going to have the next midterm and the final exam?
Oh, I don't remember, but you can double check it in this manual
It
document.
says tomorrow. It says tomorrow.
Tomorrow we have midterm 2.
Midterm 2, yeah? Oh, okay.
Yeah. Check on Moodle. I sent a message on Moodle to all students.
Oh, okay.
So there is like information about this upcoming midterm 2.
Okay, thank you.
Yeah, it will be tomorrow. There will be 7 problems. There will be 60 plus 10 bonus minutes. So it will be 70 like minutes in total to solve this. And be aware that there will be also questions from our last topic we considered before, discussed before the fall break, which is angular momentum, torque, kinetic energy of rotational motion. So vector product, because you need to calculate torque. So it's vector product of force and radius vector. So go for that and double check that you practice in solving these kind of problems, because they will be also included in this midterm too. Okay.
Thank you. Goodbye.
Have a good evening. Bye-bye.